many thanks for this nice introduction, and also I would like to express my gratitude to organizers for inviting me to give a talk, especially to Professor Tuomas Orponen. So as you can see, that my talk is partially based on the joint work with Giona Veronelli from University of Milano at Bicocca. And as Tuomas introduced, the title contains a number of notions, but they are all linked together by some monotonicity formulas which are behind them. So let us start with the isoperimetric inequalities for level curves. And let's begin with some legendary approach, namely the classical isoperimetric inequality goes back to Dido and Virgil in the 1st century before Christ, and according to the legend, relates the length of a given closed curve with the area enclosed by this curve. And I allowed myself to illustrate this legendary origins of the isoperimetric inequality by a painting by William Turner. So I suppose here you can see Dido, who is applying isoperimetric inequality, although she is probably unaware that she is applying it. But mathematically speaking, the classical isoperimetric inequality can be formulated as follows. So consider an open set in the plane enclosed by the curve, and denote by A the 2 Hausdorff measure of set omega, and by L the first Hausdorff measure of the boundary of this set. Then one can show that the following inequality holds, and this inequality is called the isoperimetric inequality. What is important is that equality here holds for a circle. And there are many other approaches to isoperimetric inequalities. For example, if one considers the complete Riemannian manifold of dimension n, then there exist constants alpha bigger than 1 and I alpha bigger than 0, such that the following inequality holds for any closed smooth submanifold n, where here we consider a Riemannian volume of n, and here the surface area. It's quite peculiar that this inequality is equivalent to a Sobolev type inequality for smooth, compactly supported functions on manifold M. And there is another approach to isoperimetric inequalities which relate them to partial differential equations. And in order to introduce this approach, let's first start with a simple case of sets in the plane, and consider D0 and D1 planar convex domains, and define a convex plane ring, also called annulus, D. Then for a C2 function on such annulus, consider the function L of t, which gives a length of a level curve and is defined in the most natural way as integral over the level curve of function identically equal to 1. For such function, Longinetti in 1988 showed that if U is a C2 function inside the ring and continuous on the closure of the ring, and it solves the following Dirichlet problem for the p-harmonic equation with constant boundary data, then this function L of t, the length of a level curve, satisfies the following inequalities. When p is equal to 2, this inequality states that the logarithm of L is a convex function, while for p different than 2, we have the following observation that a power of L of t is a convex function. And what relates these inequalities to isoperimetric inequalities in the geometric meaning is that equalities in both inequalities here hold if and only if a level curve is a concentric circle. In the same paper, Longinetti also gave a similar inequality for the following Dirichlet problem with Laplacian and function f, a non-decreasing function in annulus with constant boundary data. Then he proved that the following estimate can be found. And again, the equality holds if and only if a level curve is a concentric circle. A significant extension of Longinetti's approach is given by Alexandrini, who was able to give up the assumption about the convexity of components d0 and d1, and also extended Longinetti's approach to a-harmonic equations in the following form. And then his isoperimetric inequality reads as follows. Here, alpha is a parameter depending on the growth of operator A. And equality here holds for circular annulus and for a properly chosen p-harmonic function with p depending on the growth of parameter A. And let me also remark at this point that the problem that we consider, this Dirichlet problem with constant boundary data on annulus, is a variant of the capacitary problem of finding a properly regular function, usually in an appropriate Sobolev space, such that the p-harmonic equation or more general elliptic operators can be solved in annulus subject to constant boundary data. And this problem has been studied in various contexts. For example, for p-harmonic function in Euclidean setting, it goes back to John Lewis, also in some recent papers to Fogagnolo, Mazzieri, Pinamonti, as well as in a series of papers by Jacques Xiao. Moreover, one also studies this p-harmonic Dirichlet problem on Carnot groups, and then I would refer to a paper by Dragoni, Garofalo, and Salami. Such a capacitary problems also appear for harmonic functions on space n-forms. And this is a paper by Ma and Zhang. Okay, so in order to complete the introductory part of the isoperimetric inequalities, I would like also to give one more observation for p-harmonic mappings. Namely, we would like to see if there is an isoperimetric inequality for a component function of p-harmonic mapping in the plane. And for this, I need to recall the definition of p-harmonic mappings. Also, we will use p-harmonic mappings in the last part of my presentation. So we say that a Sobolev map U with component function U1 and U2, a map which goes from the open subset in the plane into the plane is called p-harmonic if it satisfies the following system of equations, with du denoting the Jacobi matrix of map U. This means that rows of matrix du are the gradients of component functions of map. When p is equal to 2, we retrieve harmonic mappings. And if you haven't seen such mappings before, let me just briefly mention that they appear in many models, in nonlinear elasticity theory, fluid dynamics, in cosmological models, in glaciology as well. Okay, so for such mappings, we need to slightly strengthen the assumption about the regularity of a map. And also we need to impose that the component function for which we're going to state the isoperimetric inequality is such that the gradient of this function is separated from 0. If we are in a setting of harmonic or p-harmonic mappings on annulus, then this property is known for constant boundary data. But here, the fact that the system, p-harmonic system, is coupled, and so all the component functions are interfering with each other, influences assumptions, and we need to assume that the gradient is separated from 0. Under these assumptions, if by L of S we denote as previously the length of a level curve, we may show the following inequality for p equal to 2, which is the same as for the harmonic functions. And if p is not equal to 2, we have a slight modification of what Longinetti proved, with constant c depending on the LP norm of the differential. And moreover, the equalities are attained if the second component function is identically 0 or they are equal to each other, and for circular annulus. If this happens, then U1 turns out to be a radial p-harmonic function. Of course, whatever is here stated for U1 could be as well formulated for the second component function. Okay, so now I would like to focus on the key part of my presentation and look at the isoperimetric inequalities on Riemannian 2 manifolds. So first we need to define the Dirichlet problem, which, as you will see, is quite similar to the one investigated by Longinetti Alessandrini. So let M2 be a two-dimensional Riemannian manifold with Gaussian curvature denoted by K, and we allow K to vary from point to point. Then by omega1 and omega2, we denote two simply connected domains with boundaries gamma1 and gamma2 respectively. For the first part of my presentation, we may assume that these boundaries are C1 alpha regular, but you will see that this can be weakened to just assume that gamma1 and gamma2 are Jordan curves. Nevertheless, for the moment, we will consider harmonic Dirichlet problem in the annulus, and we'll look for a continuous up to the boundary harmonic solution to this, the following problem in the annulus with constant boundary data, and for the Laplace-Beltrami harmonic operator. Then with the same notation as in the planar case, so by denoting by L of t the length of a level curve, we may prove the following isoperimetric inequality. If omega is a C1 alpha annulus in manifold M2, such that the Gaussian curvature restricted to this annulus is non-positive, then for a solution to the Dirichlet problem that we just formulated, the following isoperimetric inequality holds for all t between t1 and t2, and the equality in this inequality holds for some t if and only if the Gaussian curvature is identically 0, in which case all level curves of function u are concentric circles, and omega is a circular annulus in the plane. So if you compare it to previous results, the key difference is the appearance of the Gaussian curvature and the condition that it is non-positive. So few words about the sketch of the proof. The first step is to observe that under our assumptions, the gradient is non-vanishing. So if M2 is a manifold and U is a harmonic function which solves the Dirichlet problem in annulus, then it holds that the gradient is non-zero in annulus. However, observe that there is no assumption about the curvature in this lemma, as indeed the proof of this lemma does not depend on the curvature, but actually on the fact that we are in two-dimensional setting, which I will address in a moment. This lemma is widely known in the literature. For example, for planar elliptic PDEs, it's due to Hartmann and Wintner, who were using harmonic approximation. For p-harmonic functions in Euclidean setting, it's due to John Lewis, who studied it on convex rings and used the barrier arguments. And in the setting of manifolds, in the special setting of space n-forms, for harmonic function is due to Ma Zhang, who adapted Lewis argument. Our proof of this lemma relies on the knowledge about the topology of critical points in dimension 2 for harmonic functions, and and also relies on the structure of level sets in the vicinity of critical points for harmonic functions in the plane. And if you are interested in this problem in setting of R3 or higher Euclidean spaces, then this approach will not work. So this lemma with our proof cannot be easily extended to higher dimensions. And if you are interested in some references about the higher dimensional case, I would refer to papers, for instance, by Enciso and Peralta Salas and Roberto Magnanini's survey. Step 2 of the proof relies on the observation that if the Gaussian curvature K on annulus is non-positive, then we may show that the logarithm of the magnitude of the gradient is a subharmonic function, which combined with the minimum principle and Hopf lemma allows us to infer that this minimum of the gradient is bigger than 0 also on the closure of the annulus. In fact, the first observation about the subharmonicity is a special case of a more general lemma, and I would like to state it for your curiosity. If omega is a domain in a 2-manifold and use a harmonic function in omega, here omega need not be annulus, then the Laplacian of the log of the magnitude of gradient U is equal to the Gaussian curvature at points where the gradient does not disappear. The proof of this observation follows from the refined Kato inequality and from the Bochner's identity, here stated for general n manifolds, but in setting 2, this Ricci curvature is the same as Gaussian times a square of the gradient. And the last step of the proof for isoperimetric inequality is the following. We may show that the first derivative of the length with respect to parameter t and the second derivative of L with respect to t, they satisfy the following inequality. And this can be done by direct computations. If this is obtained, then this is equivalent to the assertion. So everything boils down to being able of computing L prime and LBs. And in fact, the formulas for such derivatives can be found on n-dimensional manifolds, as the following lemma states. Suppose that U is a harmonic function such that the gradient is non-zero in the annulus omega, and U solves the constant boundary Dirichlet problem with constants T1 and T2. Then for all T between T1 and T2, L prime can be computed by the following equation, which is equivalent to the second formula. And moreover, we have the following inequality for the second derivative of L. But if omega turns out to be a domain in a 2-dimensional manifold, then this inequality takes the stronger form of equality. So on 2 manifolds, we have the following identity. And if you combine LBs with equations for L prime and use some standard inequalities, then you arrive at the assertion of the isoperimetric inequality. But what is also quite interesting is that the isoperimetric inequality in that setting can be used to characterize open surfaces with negative curvature, since we have the following observation. If M is an open surface with Gaussian curvature non-positive in M, then for any topological annulus, we may show that the solution to our Dirichlet problem obeys the isoperimetric inequality. And also opposite. If for any topological annulus on M, the isoperimetric inequality holds, then we know that K must be less or equal than 0 in M. And there is yet another observation related to isoperimetric inequality, namely that it can be given a more quantitative formulation under slightly stronger assumptions. So let M be a complete non-compact surface with Gauss curvature satisfying the following inequality with kappa 1 and kappa 2 greater or equal than 0, and suppose that U is a positive harmonic function. Then in our setting of annuli, we may show that the following inequality holds. And if you wonder why we impose this extra assumption about the non-compactness and positivity of a harmonic function, it's because in the proof of this theorem, we use the following inequality, which has these two assumptions. So this is everything I wanted to say about the smooth case. But one also considers the non-smooth surfaces, and then it's tempting to pose the question if one can consider the counterpart of the isoperimetric inequality on singular surfaces. And it turns out that such a counterpart exists, but before I will formulate this result, we need some definitions introducing the objects. Namely, we need to define or recall definition of Alexandrov surface, also known as surfaces of bounded integral curvature, or big surfaces for short. And so suppose that S and D is a compact topological surface S endowed with a metric D, such that in this metric S is a geodesic metric space. Then the surface S said to have a bounded integral curvature if there exists a sequence of smooth Riemannian metrics Gj such that it satisfies two conditions. The first condition is that all the integrals of the absolute value of Gaussian curvature with respect to metrics Gj and with respect to the Riemannian area measure are uniformly bounded. And the second condition, that the distances dj induced by the matrix Gj uniformly converge to D, to the underlying metric D. And by uniform convergence, I mean that the supremum distance of dj's and D goes to 0. The unique weak limit of the sequence of the following measures is denoted d omega and is called the curvature measure of the Alexandrov surface, and it turns out to be a radon measure. As you see, the definition is perhaps not the most natural one, but I would like to assure you that there are many approaches to big surfaces with highly non-trivial equivalences. And one of them, for example, is to consider a polyhedral approximation instead of the Riemannian approximation. And indeed, this is the original approach of Alexandrov. And also, the curvature measure can be defined in a more geometric way as an outer measure, and this definition is based on the Gauss-Bonnet theorem. In any case, these equivalences and different definitions of the big surfaces are very well introduced and described in a series of papers by Mark Troyanov, and also in a survey by Reshetniak. So, do we have many examples of Alexandrov's surfaces? It turns out that, for example, compact polyhedral surfaces satisfy the definition of Alexandrov surfaces, locally cut zero surfaces as well. Moreover, compact metric surfaces with lower bound curvature in the sense of Alexandrov, which in particular means that the compact Gromov-Hausdorff limits of surfaces with lower bounded Gaussian curvature as well are Alexandrov's surfaces. And this is well described and explained in a book by Burago, and Ivanov. Also, some more recent advances in this area show that RCD surfaces are Alexandrov's surfaces, and this can be found in a paper by Witczak and Stadler. RCD spaces, without stepping into the definition of this, are the successful approach to study the metric spaces with the counterpart of the Riemannian geometry on it. And RCD stands for the Riemannian curvature dimension condition. And finally, the list of examples closes with surfaces with conical singularities. And by this we mean smooth Riemannian surfaces which, apart from with a discrete set of singularities, where locally the metric structure is equivalent to the one of the Euclidean cone. All right. So, what is a counterpart of the isoperimetric inequality in that setting? So let SD be a closed surface of bounded integral curvature with non-positive curvature measured d omega, and then let omega be a non-degenerate topological annulus with boundary components being the Jordan curves. In such setting, we consider the Dirichlet problem with constant boundary data for the Laplace-Beltrami operator on the surface S. And first of all, we may prove that there exists a unique continuous up to the boundary solution of this problem. And moreover, it turns out that the length of level curves satisfies that the logarithm of L of t is a convex function on interval t1 and t2. So this is the clear counterpart of the isoperimetric inequality in the smooth setting. And the proof of this theorem relies on a number of observations. The key one is the following. As I mentioned, there are many definitions of Alexandrov surfaces, and one that is quite fruitful in consequences is due to Reshetniak and Huber, who proved that who defined Alexandrov surfaces as a conformal deformations of smooth Riemannian surfaces. And this means that one can construct a smooth Riemannian metric H, which gives a metric equivalent to the underlying metric D. Then the curvature measure, d omega, can be represented as the weak Laplacian of a properly defined distribution. Also, the non-positivity assumption on the Gauss curvature measure corresponds to the Gauss curvature K being non-positive. And finally, when one computes the logarithm of L of t, it helps to observe that the function L of t can be expressed as a line integral of the x of a conformal factor for the flat metric corresponding to H. So in fact, we do two changes of a metric. First, for D, we choose this smooth Riemannian metric, and then we uniformize annulus and choose a flat metric whose conformal factor is then used in computations for L of t. Okay, so this is everything about the isoperimetric inequalities. And now we remain in the setting of manifolds, but would like to focus on the curvature of level curves. And so let us first recall some notions from the planar setting. Suppose that U is a C2 function in an open set in the plane, then the curvature of a level curve is defined as follows at points where the gradient of U is non-zero. And this formula follows from the direct computations for the sine curvature of a planar curve and of course makes perfectly sense outside of the level set, as long as the gradient is non-zero, but the geometric interpretation as a curvature holds only for the level curve. And for such curvatures, the following observations were made by Talenti. If U is a harmonic function with no critical points in a given domain, then the normalized curvature of the level curve, so this curvature Ku divided by the length of the gradient, is a harmonic function. And the minus logarithm of the absolute value of this curvature is a subharmonic function. Of course, when you now move to the setting of manifolds, then some modifications must be made. But it turns out that when defining a counterpart of this expression on two Riemannian manifolds, one can localize the discussion, introduce a local orthonormal frame, and compute the covariant derivatives with respect to that frame. One obtains an expression similar in symbols, in terms of the symbols, to the one in the plane, but with slightly different geometric meaning. And it turns out that the analogs of Talenti's observations for planar harmonic functions can be proven for Riemannian two manifolds as follows. If omega is a domain in a Riemannian manifold with Gaussian curvature K, not necessarily constant or of constant sign, and U is a harmonic function in domain omega with no critical points in omega, then the normalized curvature of level curves satisfies the following differential equation. And you can see that when the Gaussian curvature K is identically zero, this equation reduces to the harmonic one, and we retrieve the Talenti's result. And moreover, the following inequality holds for the minus logarithm of absolute value of K, with the same observation as previously, that for the zero Gaussian curvature, we retrieve the Talenti's subharmonicity result. Few remarks and applications of this observation. Let me observe that the previously stated result is known due to a paper by Wang for constant Gaussian curvature two manifolds. And we extended it to the setting of non-constant Gaussian curvature. And also similar PDE and differential inequality can be obtained for the curvature of curves of steepest descent. I would like not to step into the details of this, but one can consider the lines which are orthogonal to level lines and define the analogous curvature for such lines, and it's called the curvature of the steepest descent. It behaves in many ways in a similar manner as the normalized curvature studied in this theorem. Perhaps the consequences of these equations and inequalities are more interesting than equations itself, because the corollaries of the theorem encompass a number of maximum and minimum principles for this expression. For example, if U is a harmonic in a subdomain with no critical points, then under proper assumptions on the sign of Gaussian curvature and this expression, one may show that absolute value of K attains its minimum on the boundary of the domain. And a number of similar results can be found in my paper with Giona, to which I will refer in the end of my talk. So in the last part of my presentation, we return to the setting of p-harmonic mappings, this time in Euclidean setting of Rn spaces, and would like to see if we can have three spheres theorems for coordinate functions of p-harmonic mappings. But let's begin with recalling some history. If V is a subharmonic function in the plane, and we denote by M of R a supremum of this subharmonic function over a circle centered at origin with radius r, then for three concentric circles, R1, R, and R2, we may show the following inequality, which can be seen as a statement that this maximum M of R is a convex function of logarithm of radius R. And this theorem was stated by Hadamard in a letter to a friend and proved something like 20 years after this letter was sent. Hadamard didn't bother to provide the proof. And one of the reasons for this is that the proof is quite straightforward. It relies on the comparison principle for harmonic functions and the formula for the fundamental solution for Laplace equation in the plane. Nevertheless, the corollaries of this theorem enclose the Liouville theorem for subharmonic functions in the plane and a number of other observations. The Hadamard theorem enjoys very many generalizations. First of all, one can generalize it to higher dimensions, n equals 3 or higher, and then the three spheres theorems can be expressed as that a maximum M of R is a convex function of power of the radius R to 2 minus n, which is a clear consequence of how the fundamental solution for the Laplace equation looks like in dimensions 3 or higher. One can also study surfaces other than spheres, as well as differential operators other than the Laplacian. Some second-order elliptic PDEs, quasi-linear PDEs, including p-harmonic equations, Riccati-type equations, as well as heat equations. In the latter case, the three spheres theorems is known as the three parabolas theorem. But there is yet another approach to the three spheres theorems, namely for some L2 and L infinity norms and for solutions to some elliptic PDEs, the following observation can be proven. With parameter alpha, depending on the ellipticity constants of the equation. And if you recall lectures from the previous week, this type of inequality appeared in one of the lectures by Professor Malinnikova. And it plays important role in the studies of the unique continuation property. So let's address the question if we can study the three spheres theorems for a given coordinate function of a p-harmonic mapping in Rn for n at least equal to 2. For this, recall that the p-harmonic mapping from a set in Rn with values into Rn satisfies the following coupled system of equations. And so problems that we need to overcome in our studies include the fact that the differential appears in all equations of the system, and so all component functions interfere with each other. And also there is no fundamental solution nor comparison principle involving only single coordinate function of a p-harmonic mapping. So what we may do? First, let us choose and fix one coordinate function, for instance, U1. Whatever I'm going to present from now on can as well be stated for all other component functions of the p-harmonic map. Denote by M of R a supremum of this component function over a sphere centered at x0 with radius R. And then let us formulate the three spheres theorems. First, suppose that P is between 1 and n, and consider three concentric balls such that the largest of it is enough far away from the boundary of a given domain, and also that radii of balls are in a sense comparable. So we would like to avoid situations that, for example, two spheres are close to each other and the third one remains in a further distance from the previous two. We need to split the discussion depending whether p is between 1 and 2 or bigger than 2. In the first case, we assume that coordinate function u1 grows faster than a power function outside of the largest ball, while for p between 2 and n, we assume that the gradient of u1 is separated from 0. And then under these assumptions, we may show that there exists a constant c and a radius r3, so that the following three spheres theorems holds. It's quite important to understand what are c and how r3 is chosen. So let's see. For p between 1 and 2, a constant c depends on the usual parameters and the LP norm of the differential, and r3 is bigger than r2. But for p between 2 and n, r3 is equal to r2. So in this case, we do retrieve the proper three spheres theorem. Of course, when p equals 2, we don't need any growth assumptions on u1, r3 is equal to r2, and we retrieve the known result for harmonic functions. Since my time is almost up, let me very briefly say a few words about the main ingredients of the proof. First ingredient is due to Uhlenbeck and Torgsdorf, who proved the following estimates for the supremum of the differential of u, and they follow from the fact that a power of the norm of differential satisfies is a subsolution to elliptic equation, from which the supremum estimate follow. The second ingredient are the Cacciopoli type inequalities for coordinate function composed with a proper convex function. And the third one, perhaps most important and probably maybe even more interesting than the three spheres theorem itself, are the De Giorgi type estimates on superlevel sets for coordinate function u1 composed with this convex function phi. And for the details of my presentation, I would like to refer to the following publications. The isoperimetric inequality on surfaces and the curvature of level curves are discussed in a work with Giona Veronelli. Isoperimetric inequality for p-harmonic mappings can be found in paper number 2, and the three spheres theorems for p-harmonic mappings are discussed in paper number 3. And I would like to thank for your attention.